Good afternoon, and thank you for staying late. And my name is Tao Wang, and so on behalf of our team, I would like to talk about the findings of our project. And so I'm going to talk about air pollution. So I'll talk about mainly on some of the scientific findings and also the impact on policy. We don't do too much of technologies or products, but our implications would be hopefully influencing the policy on air pollution control. So this project was undertaken by four researchers from 4 universities, local universities, and the Environmental Protection Department, and 2 outside institutions from mainland and from Germany. And sorry. So first, let's briefly review the project objectives and slope and scope. So air pollution, we know it's a big environmental issue, and so we have many pollution sources that emit the so-called primary pollutants, including all these chemicals, and they create local problems like roadside, that the dirty air we breathe. But here I want to mention that these pollutants also undergo dynamic sort of transportation and also undergo chemical conversion. And through the chemical reactions, they create a suite of so-called secondary pollutants, including ozone and fine particles, or we better known PM 2.5. And so we have in the atmosphere, we have also many oxidants that act to convert these primary to secondary pollutants. So our project focuses on this, the secondary pollutants, which turned out to be more difficult to understand in terms of formation and also in terms of development control measures. And by the way, the ozone is one of the pollutants in Hong Kong. It still keeps rising, where other pollutants have been improved. And the PM is a big problem also here and also in mainland China and many cities. So this is the sort of brief introduction. So our project is we think it's a new paradigm. Basically, we wanted to integrate the urban pollution with the pollutants emitted from our natural environment, including trees and soils, and also our oceans. So Hong Kong is nearby the ocean. Ocean is good, for many things, but you can also enhance the air pollution. So I will show you. And these pollutants, they mix together and create what we call both primary and secondary pollutants. Hong Kong also has another challenge in terms of air quality that we have, on the one hand, we have a local pollution problem, but also have a regional pollution problem. But these two can interact both dynamically and chemically. So how to address this coupling is a very, very big challenge. So this is something that this project will tackle. So we will try to understand this complex multi-scale processes and photochemical pollution, and we also hope to recommend evidence-based mitigation strategies. Here, this project has 5 core areas. So first we'll deal with the emissions, where the pollutants are coming from both urban and natural sources. And then very important part is to understand how these primary pollutants are converted to the so-called secondary pollutants like ozone and PM. And then we also want to look at the urban and local interactions. And very important task is to also how to translate the findings into policy. So these are the 5 core areas. So next I will report the project findings and impact we generated so far. And our project has, this is the 5th year, near the end of the 5th year, so we have another year to go. We extended for 1 more year due to the COVID situation. Okay, so first finding where the pollutants are coming from. So we look at the emissions from our natural environment. Nitrogens can be emitted from soil, both fertilized and unfertilized soil. So this has not been looked at before. And so we took a few soil samples from Hong Kong and other places in China and tried to measure the flux and derived the so-called parameterization and put into computer models so that we can estimate the impact of these soil emissions. And also the emissions from trees or subtropical vegetations, that this part also much understudied. And so we measure the emissions of the highly reactive organic gases from different vegetations, and then again put into the model. So this also improved the performance of the model. Another class of chemicals that are not well studied is this halogen, chlorine and bromine compounds. And then, of course, the big source is from the oceans. We all know sea salt. But also, human activities also emit these halogen compounds. This is the first time we developed this high-resolution so-called emission inventory for these hydrogen halogens. So all these newly developed sort of emission database have been integrated into so-called the urban emissions. So now we have very comprehensive sort of database to drive our air quality models to better predict the air quality. So this is on the emission. And on the chemical reactions, and this is very, very important, that here we know that the main oxidants in the atmosphere is the so-called OH radical or hydroxyl radical. But in addition to this so-called conventional radical that can drive the oxidation of many reduced gases like VOC that can generate ozone. This is our big problem. And also a large fraction of the PM 2.5. And this creates a haze problem. So the issue is that we don't know too well about what sources that generate this OH radical. Moreover, that there are potentially so-called new radicals that can play the same role, speeding up the oxidation process. So these are the so-called new radicals, and this project actually has some breakthrough in understanding these. So in terms of research approach, that we, as any geoscience research, we need to do observations. So we conduct measurements, ambient measurements, different environments, that roadside to look at the roadside pollution, and oceanic side to look at the pollution interaction, the natural and sea salt emissions. We also go to the forest environment to look at the pollution interact with our vegetated environment. And so this is so we have a lot of findings ranging from a missing source of the OH radical to the new discovery of halogen radical, and also the new pathways for organic formation, etc. Due to time limit, later I will only highlight two such findings in a while. So in addition to ambient observation, we also do laboratory simulations. So this allows us to better understand the formation mechanism of air pollution under controlled environment. So in the atmosphere, it's open. It's very difficult to control the parameters. So we use different small and large chambers to look at the chemical production process. So in addition to experimental approach, that we also have to use models to look at the impact of air pollution and also to predict the pollution. For example, here the model show that the previous speaker showed that we have this dead zone, but here we have very highly polluted area over the Pearl Estuary on ozone, and so there's a pool of ozone pollution there. So Next, I will highlight two findings. I want to make sure that I don't overrun. So one is I want to report the discovery of a new chemicals that can aggravate the pollution in the coastal environment, like Hong Kong. So halogen compounds are not new, and they were first known for their role to destroy ozone, good ozone, in the stratosphere in the both south and north poles. But in the outside the polar regions, previous studies only focused on this chemical that can this chemical can actually aggravate air pollution. So this is called ClNO2. But there have been very little studies or little known of other halogen compounds outside the polar regions. Okay, so in a few years ago, our project organized a very comprehensive, so the multi-party participated field observations at one of the site here in Hong Kong. This is managed by the Hong Kong EPD, has a very good, excellent facility that to accommodate a large number of equipment. A lot of this equipment are state-of-the-art, and they can measure very precise chemical compositions so that which allow us to deduce the formation mechanism. So here we use also a very sophisticated instrument for measuring the halogen compounds. Very difficult to measure, but through research development that we are able to do them. So the finding, so we observe very surprisingly, very high concentrations of this molecular chlorine. Molecular chlorine is very easy to photolyze. So under the sunlight, it should go immediately, it should go down immediately or disappear. But instead, this chlorine climbed to very high levels in the middle of the day. So this suggests that there's some source previously unknown that produce these highly reactive chemicals. And so we look through the current sort of mechanism, chemical mechanism that were proposed to explain the polar halogen chemistry, but they could not explain that why it's so high here. And so we need to find what is the underlying process. So in short, that through the field analysis of the field observation and also laboratory controlled experiments, so we found that the photodissociation of nitrate, aerosol nitrate, that under acidic conditions can produce very high levels of molecular chlorine. Okay, so this is and we calculate that this source can explain the observed high concentrations in the coastal environment here. And so what is the impact? What is the importance of this high molecular chlorine? So through chemical model analysis, so we can see that this chlorine atom from ClNO2 can actually enhance the oxidation capacity of the atmosphere, enhancing sort of ozone production of like 16%. So that's quite a lot. So basically, this chemical can enhance the power of our oxidation and then enhance the production of secondary pollutants. So this is a sort of conceptual model we propose. So we have land-based emission coming from the cities and interact with sea salt particles. And then these chemical reactions activate inert chloride to active or reactive chlorine species and then drive the production of secondary pollutants. So we think this is a new mechanism, can be important in other coastal environments, cities. So this work actually has attracted a lot of interest from researchers outside our team. So we jointly published the findings at this very good journal. And later in the field study, not only the Cl2, but we also found very high concentrations of another bromine compounds. So this, again, peaking at very high levels during the daytime And through the same through laboratory studies, we found the same mechanism can also produce very high molecular bromine compounds. And then this actually add additional impact on our productions of secondary pollutants. In addition, that bromine can produce very high toxic mercury 2 compounds. And so this can shorten the elemental mercury lifetime from 40 to 4 days. So this can potentially have threat to our seafood safety. So this is something coming out from the potential impact of this very high chlorine species. So this is sort of findings in the coastal environment. We also found that during the coal burning season in wintertime in northern China, that we also found very high concentrations of this compound, BRCL, or bromine chloride compounds. This is the first time that we observe, or the community observes, such high concentrations outside the polar region. And again, in the interest of time, I'll not go to the detail, but we propose this mechanism. The coal burning can emit not only other conventional pollutants, can also emit reactive halogen gases. And this actually has not been recognized before. So we suggest that further control coal burning will have definitely an additional benefit that this has the implications later I will show. And again, this result also attract a lot of interest from the community, and we publish this in the high impact journal this is a new journal. So we also put into the model and calculate what's the impact on haze. That's a very big problem in northern China in winter time. So you can see all this red area, indicating the enhancement of haze pollution due to the halogen source from the coal emission. So basically, there are some policy implications on the result that we think that we should, future air pollution control should consider halogen, which is not regulated right now, but future work, maybe we need to control this. Second implication is that we suggest that we should further strengthening control of the 2 conventional pollutants, because this will also help to reduce the halogen production and therefore reduce their adverse effects. So another highlight of our photochemical studies is the discovery of new production pathway of organic aerosols, organic fraction of the PM2.5, and SOA in short. So this SOA the production is pathways are very complex, and we have multiple proposed pathways, but they are not very well quantified. So in the same field study that our team used another very highly sophisticated instrument and measure many organic compounds at the molecular levels. And with this data, we'll be able to find the source of these many organic oxidation products are coming from aromatic and also the long chain hydrocarbons. And this also has not been known before. So that means in order to control these organic compounds, we should target these two. These two mainly coming from vehicles and also solvent use, etc. And so this actually organic compounds contribute to up to 70% of the organic component of the PM2.5. So this actually, of course, is very important for science, and also for the air quality management. And so this work is, again, very attract the interest of the community and through collaborations, and this work has been published in Nature Geoscience. And so I think this is very important. And next, I will talk about findings on the regional and local interactions. So our project has developed and applied a suite of sort of multidimensional models, not only the large-scale or regional urban models, but also down to very fine-scale models to resolve buildings, because this is fine-scale models are particularly important for high-density cities like Hong Kong. We have a lot of high buildings and also complex topography, mountains and shorelines. So because this is the high-resolution models are needed to address this so-called segregation effect. For example, in Hong Kong, that our emissions are emitted along the coastline, but we have mountains area. So the emissions are emitted separately in different places, but how to simulate or deal with the mixing of these two segregated sources requires high-resolution model. So the team developed this high-resolution model now down to scale 30 meters, and then which allows us to simulate pollutants movement in a small area like the Kowloon Peninsula, which cannot be done by conventional regional model. And also in order to resolve the movement or processes around the buildings, and our team also developed the so-called building resolved models. And these models actually can be used for, maybe to assist the better urban design down the way. So these are the models. I want to watch out the time here. So next I want to talk about what are the findings, how can they be used for policy or for to develop a better or improve the air quality management. So first item we did was that we want to evaluate so-called the effectiveness of the so-called Clean Air Action Plan. This is a national initiative, so you know that since the discovery of the PM 2.5 in about 10 years ago, Chinese government launched very aggressive, unprecedented emission control. So during this period, 5-year period, and then a lot of the emissions have come down a lot, especially for sulfur. You can see sulfur and some nitrogen, and also the primary emissions of PM have also come down a lot. And ambient air quality also responded positively. And so you can see the measured concentrations of most of the pollutants also did improve, except this ozone I mentioned several times. Ozone actually has been increasing in urban areas. So this created a dilemma or the confusion to the policy community. So what is the reason of this? This actually, for those who study atmospheric chemistry, you know that ozone is formed by the nonlinear sort of reactions between NOx, nitrogen, and VOC. And but we want to demonstrate what is the reason. And also, ozone is also affected by meteorological conditions. So the weather can play a role. So in this study, we use a computer model, try to separate the effect of the meteorology, weather change, and the emission change on ozone, increasing ozone. And we found, indeed, the meteorology is very important. So we should not just look at the emission change, and try to look at the ambient, the air quality response, but also we need to take into account of the weather change. And so you can see the red, meaning the meteorology weather change contributed to increasing the ozone. And the emission change actually in those past five years, which target to PM, indeed helped to reduce PM, but they did the opposite. They have a negative effect on ozone, again, due to this, the So we look at the 4 megacities in different regions and did more detailed study. Again, this is to highlight, first, weather change is important, and you need to consider this, and also the emission, PM targeting emission control actually has a side effect on ozone, okay, due to the complex chemical, so-called the nonlinear properties, and also the effect of aerosol. Decreasing aerosol can promote, okay, promote the ozone pollution. So this demonstrates that. So every people think, oh, after reducing the pollutants, transportation, we should have clean air. But for the secondary pollutants, ozone in particular, that it has very complex sort of response. So in short, that we recommend that we should also control another group of chemicals, that is volatile organic compounds, together with SO2 and PM. So this is the recommendation. So we did similar study for Hong Kong, and again demonstrate this is the same process occurring locally. And another study is that this was not proposed in our proposal. So pandemic came, that so this created opportunity for us to, or unprecedented opportunity for us to test our understanding how pollutants respond to the huge reductions in human activities and also the air pollutants, right? So here, our project team actually look at the response of secondary pollutants like ozone globally and also in China and also Hong Kong. And again, to show that ozone, unlike other pollutants, can increase or decrease during the pandemic. Again, due to this very complex chemical sort of interactions. And more recently, we look at the lockdown in Shanghai, just happened 6 months ago. So the previous lockdown was in the winter time. So at that time, generally, photochemical pollution is not so strong. But here, in this recent lockdown in Shanghai, that took place in the warm season, in high ozone season. So what we learn here would be more sort of useful to dealing with the ozone problem in the summertime. So some statistics show that we have huge drops in human activities. But look at the ozone here, the red. And it actually, and this is NO2, the vehicle NO2 dropped significantly, right? But ozone increased. Again, because of time, I cannot elaborate. In short, is that this high ozone is due to the larger reduction of NOx than VOC. So, and this actually is not ideal for, it's good for other pollutants, but not good for ozone. So we need to, for ozone, we need to have different strategies to control. So basically, we need to control more of VOC in order to also reduce the ozone pollution. So our project also have looked at the impact of air pollution and for both ozone and PM. And so basically this study is worth highlighting here that so despite we have increasing ozone, but the overall effect from the decreasing PM, decreasing nitrogen, and the overall effect actually has been improved. The health effect has been improved, for example, especially at the roadside. And these are the general station, has not worsened, at least in Hong Kong. Okay, so this is I think has important also so basically the message is that even though ozone increased, but the overall health effect has not been worsened. But still we need to deal with the ozone problem. Okay, so after 5 years research, we need to publish, of course. So we have, I think we have achieved a quite good result, including publication in several high-impact journals. And also, very important sort of activity is to disseminate the findings to the larger, wider communities. So we exchange the findings in different sort of professional bodies, and also the embassy, the Swedish embassy personnel, and also the office of government officials. So we especially we exchanged our findings on with the Hong Kong, nearby Shenzhen, Shanghai, and also the ministry people, that to help them to develop so-called co-control of PM and ozone problems. And for example, our study has shown some impact, and our project finding has supported the control, the newly initiated ozone control during the summertime in mainland China, so in the past 2 years. So our findings have helped them to, okay. And GBA study also in the EPD, and here we also, some of our members sit on the air quality review science panel to tighten, hopefully to tighten the air quality standards for our next 10 years. And so we also disseminated the information to the news media. And we definitely have trained a new generation of scientists. And in particular, one of our recent PhD graduates got the only Polio Outstanding PhD Thesis Award. She's now working at the Ministry of Environment in China, hopefully to bring the research expertise to air quality management. So in very short summary, so we don't read it very long, but in terms of science, we have several breakthroughs in fundamental understanding, and in terms of policy, we have sort of contributed to policy evaluations and also recommendations and capacity buildings. We have developed the strong local collaborative team, and also very, very strong international collaborations. And so I want to say that the tools and the personal resources that we developed are going to be very useful for Hong Kong and for China, especially they are now targeting ozone for the first time. Before they focused on PM, but now it's the national policy that they want to tackle the ozone problem. So our team will be ready. We already helped them, but we'll continue to contribute to and also to the carbon neutrality sort of initiative goal. So with that, I want to thank our team members, and we have also project advisors and collaborators for their contributions and advice, and also thank you for your listening. Thank you.
Thank you, Professor Wang. If you have questions for Professor Wang, please raise your hand now.
Professor Wang, a very interesting, very impressive study with very important findings. Also, it's a very comprehensive study in which you studied interactions of urban, terrestrial, and ocean. So in seawater, it contains 19,500 milligram per liter of chloride and about 65 milligram per liter of bromide. So that's why, so in Hong Kong, we've been using seawater for toilet flushing for many years. So when we did wastewater treatment, because seawater is introduced into our wastewater treatment system in Hong Kong. And then we have chloride, we have bromide in Hong Kong's wastewater. After primary and secondary treatment, and then we did, now we are doing disinfection. So when we did disinfection, when we do disinfection with chlorine, we can form not only chlorinated disinfection byproducts, but also brominated disinfection byproducts. So brominated disinfection byproducts are generally dozens to 100 times more toxic than chlorinated DBPs. So interestingly, in your study, you found the formation of those halogen species, including chlorine, bromine, and bromochloride. So in the air. So that's something really interesting. So you have those chlorine, bromine, bromochloride species, and especially under the solar irradiation, they can form halogen radicals. And in the air, you have so many organic compounds. So they may also react to form a halogen containing species. So in the air, they can form some kind of halogen byproducts. So would you like to comment those potential formation of halogen species? Another following question is that, so in Hong Kong, you have those halogen species in the air, but I believe because of relatively high solar irradiation intensity in Hong Kong. So in other coastal cities or inland cities, do they also have these kind of halogen, relatively high concentrations of halogen species? And under COVID-19, so you have coronavirus in the air and other pathogenic microorganisms in the air. So if we have those halogen species, they can act as disinfectants. So they may lower the concentration of those pathogenic species, pathogenic microorganisms. So would you like to comment these related issues?
Okay, thank you. I try to remember your question. So the halogens compounds now not only from the oceans. Oceans is a big source, but they also come from various man-made sources, including the disinfectants and also power, coal burning, waste burning, and they can also emit halogens. And so yes, the sources can be widespread, not only from the oceans. So the effect, in fact, is not only only restricted to coastal environment. We have other studies showing that this activation of chlorine is taking place in many, like entire eastern China that we studied. So it's widespread issues. And organics, after, so the photolysis of this reactive halogen, they produce chlorine, bromine radicals or atoms. So these are very highly reactive chemicals. So they can react with many things, many chemical compounds in the air, including organics. So why ozone was enhanced is due to chlorine acts upon the VOC oxidation. So that process, they enhance the ozone pollutants. So we, in addition to ozone, that we also detected chlorine-containing organic gases. So that's another indication of, or another proof or evidence that this process is taking place. So we have multiple evidence to support this. So, so we think this, of course, there's still relatively limited study that other coastal environment, we think they will have a similar process. So in fact, we are also currently doing a field study in Qingdao and try to see this process occurring in other coastal cities. Yeah. Did I answer all your questions? Yeah. Thank you.
And other questions? I think Professor Guo has one question.
Solvents with critical VOC. I just wonder whether the O3 ozone creation is due to is a temporary effect increase, or you think it will continue, particularly if COVID is gone, maybe will. I mean, related issue would be to control the amount of solvents that we use.
Well,
yeah, in various
yeah, interestingly, during the Shanghai lockdown, not only traffic emissions, but also a lot of solvent use also decreased. But yet, ozone has not been improved. So this gives us some clue that in many of our cities, the pollutants are too high. They are pollutants. So even after after we halved the pollutants, that this is still not enough to achieve our ozone standard. So in other words, we still have a long way to go. I think this is one, real world case lessons we learned. And we also show that another implication I did not have time to explain before that. So reducing transportation, which is good, like using e-vehicles, our previous speaker. So I fully support that, definitely, that we do many good things, carbon, most of the pollutants. But the study in Shanghai, also in other situations, that so if you just do the transportation, that our ozone pollution may very likely worsen due to this, again, nonlinear. In some cities, not all. So we need to add additional control, especially from the solvent use or from other petrochemical industries, so that we can achieve the the improvement of everything. So in short, yeah. Okay, thank you.
Do we have more question on the back?
First one, you mentioned sulfur dioxide. What is the sulfur dioxide story in the photochemical air pollution project?
Sulfur dioxide, in terms of photochemical pollution, it has a very little direct effect because oxidation of sulfur does not produce ozone. However, in our study show that reducing sulfur has an indirect effect. Reducing sulfur, because reducing sulfur, we reduce the formation of sulfate particles. So reducing sulfate particles, we enhance the sunlight. And also, reducing particles, we reduce the uptake. In other words, I don't know how to, the reactions of reactive gases on particle surface. So this can also increase ozone. So that's why I show that decreasing sulfur emission can also enhance the photochemical pollution. So this is that's the answer. Yeah.
Any other question?
Yeah, Professor Wang. Thank you, Professor Wang, for your great contribution to our understanding of the air pollution in Hong Kong and PRD. I just have a general question here. It's not technical here. You know that you're aware that according to the Climate Action Plan 2050 here, EPD and the power companies are aiming to phase out all coal-fired power plant by 2035. And also by that time here, all passenger vehicles will be converted to EV. And maybe the medium and heavy vehicle like buses here may also be turned to be either fuel cell driven or battery driven vehicles here. So according to my casual conversation with EPD, I don't know if there's any representative of EPD here, just casual here, nothing formal here. And they say that by 2035 here, there will be no more air pollution, and our air pollution control unit will be disbanded. That's what they're saying. No more air pollution here. So I just want to have your view on whether this is true, that so far you have depicted air pollution, but if all power plants are gone, and because transportation contributes perhaps 60% of our air pollution in Hong Kong here. If they're all gone here, would the air pollution impact that you depicted to us here will disappear? But I know that the ozone will stay. I want to have your general view on that. Thank you.
So you already answered you know the answer then. So yes, most of the air pollutants, including CO2, will be gone, or almost gone. Ozone is maybe a lingering problem, because this ozone, I did not mention, is a regional or even global issue. So we have a very large background. For example, we did some study. Hong Kong is a small place. We emit a lot of pollutants, but they don't have time to produce ozone locally. So they maybe produce other places. So what we see, the ozone in Hong Kong, Hong Kong coming mostly coming from outside. So this is not to blame, shift the blame to other parties, but we say, this is all saying that we really need to have regional cooperation. We said once again, one more time, that regional cooperation with the PRD and also with the mainland government is critical. That's a good news, because finally the mainland government now takes ozone seriously. So now that they're already undertaking the serious measures to tackle the ozone. So I'm optimistic that ozone problem will also be solved in not too distant future. Yeah. So I support electrification of our transportation and our power generations. But ozone, yes, we need to take additional actions. Yeah.
We do have time for more questions. There's one on the very far end of the room.
Thanks, Professor Wang, for the very nice result and the very important discovery. For the chlorine and bromine, one potential source is especially under solar irradiation, is the PVC and the flame retardant, especially in the urban area. Do you know whether that can contribute significantly to the halogen issues?
Sorry, you said
PVC, because in the urban area we use a lot of PVC plastic, right? The polyvinyl chloride. It's a very popular plastic, and the other flame retardant mostly based on bromine molecule. Mm-hmm. Then of course under UV, under solar, all these can emit. Mm-hmm. The generate the radicals.
Mm-hmm. Yeah, those very inert. Those chemicals are very inert in the lower part of the atmosphere, so they stay very long time. So their role is mainly in the stratosphere, high, where you have a lot of strong, much higher solar radiation to break the stable molecule. So in short, that those chemicals you mentioned at the surface, Earth's surface, are inert. So they don't participate in the chemical reactions and generating the pollution here. Yeah. Thank you.
Due to time limit, I have to end this vivid discussion here. Let's thank Professor Wang again.
Okay, thank you.
With that, we'll end this morning's presentation session. There will be